So in this video, let's go ahead and talk about this new kind of problem we might want to solve called topological sort. So the area of interest, just one example, would be sorting dependencies. So for example, suppose you're trying to graduate from UW, you need to take a number of courses. Now, we might have a set of courses required to graduate, and most courses have prerequisites. So suppose that Math 126 and CSE 142 are prereqs for 143, which is a prereq for 374 and 373, and 373 is a prereq for 417. Now, notice that 126 isn't a real prerequisite for 143 in the University of Washington we all are at, but I'm just using this for an example in terms of these slides. Now, what we want to be able to do is, given this arbitrary graph of dependencies, be able to come up with an ordering for you to take courses. Let's just assume that you can only take one course a quarter. What is the sequence of courses you should take? So one possible ordering would be Math 126, followed by CSE 142, followed by 143, 373, 417, and then 374. Now, the important part of this ordering is that you always take courses such that you don't violate one of these prereq constraints. There might be multiple orderings that exist that don't violate these constraints, but we want to come up with an algorithm that, given some graph, will be able to determine one of them. Now, this problem of taking one of these dependency graphs and coming up with an ordering is called a topological sort, where we're trying to take this directed graph of dependencies and come up with an ordering that respects all of those dependencies. So the intuition here is this kind of dependency graph, where if there's an edge there, it means U must happen before V. And so any ordering here must kind of satisfy all of these constraints. Now, when we show in these slides some of these topological sorts, sometimes we'll just show the nodes themselves, A, B, and C. And other times we'll also show the edges to make it clear that this is the ordering based on the dependencies. Both of these are equivalent. The important thing is the ordering of the nodes. But I just want to mention that sometimes we show the edges to make it a little bit clear that we are respecting all of these dependencies. Now, I mentioned courses as being one possible application of this idea of a topological sort, but they exist all over the place. So for example, I already mentioned this graduating kind of, you want to take classes at UW and they have prereqs. Oops. But there's also cases where you use this when you're writing programs. So this whole quarter, every single time you've been compiling your project in IntelliJ, it's been using one of these topological sorts. What it does is it computes a graph of dependencies based off the Java files, which Java files depend on other Java files, which might depend on the libraries that we included in IntelliJ. And it computes this whole graph that it figures out an ordering for, such that it only has to recompile the parts that have actually changed. And then if you change something, it recompiles the parts down the line that depend on it. So this is a very important feature of most modern programming language development environments, to make sure you don't have to recompile the entire project from scratch each and every time. These things also show up quite frequently if you think about industries, not just tech industry, but lots of industries, where they have to encode multi-step workflows to do something. So I've worked in places where they use, they're trying to train machine learning pipelines, and they come up with these graphs that say this task has to come first before these tasks, which come up with before these other tasks. This dependency graph defines how the pipeline for how they train their machine learning model, and then they come up with an ordering for executing these tasks for whatever pipeline they come up with. So one natural question here is it always possible to come up with a topo sort for any graph? So for example, if I gave you this graph of kind of made up course dependencies, is it possible to come up with a topo sort for it? Well, I would say no, because it's not clear where you can start, right? So if you try to start with 143 and then go to 373 and then 417, that wouldn't work, because then 143 would become before 417, but there's a dependency there from 417 to 143. But in our original graph, the graph we looked at before, I would argue this did work. So think for a second, what's the key difference between this graph and above and the graph that we talked about earlier? Can you spot any key differences between them? Now, you might see here that's the fact that that first graph doesn't work because it has a cycle. So a graph will only have a topological ordering if it's a DAG. Remember, we use this term DAG to describe a directed acyclic graph. It's an important combination of the properties we talked about because it shows up so commonly, particularly in cases where you care about topological orderings. So a DAG, directed acyclic graph, is a directed graph. These topological orderings only make sense when we have a sense of direction. And this topo sort will only exist if it's acyclic. There aren't any cycles. One thing to note, though, is that this topo sort is not necessarily unique. For example, in the topo sort for this second graph down here, you can kind of swap math 126 and 142 in any ordering because they don't depend on each other. So there might be more than one topo sort, but one is guaranteed to exist in a directed acyclic graph. One thing I want to quickly mention is that the edges may or may not be weighted, but topo sort doesn't care about that. It only cares about ordering based off these direction of arrows. It does not care about edge labels. Now the question is, how can we actually perform this topo sort? How can I actually go through, given a graph, and figure out this topological ordering? So the first idea I might think of is, well, trying to go through a graph, maybe I'll use one of my traversals, maybe BFS, because that kind of goes level by level. Hopefully I'll capture all of the dependencies. So my first idea is to use BFS, but remember, BFS needs a starting point. You need to start at a particular node. And so my idea would be, well, let's start from a vertex that has no incoming edges. Because we can't start at any particular vertex because there might be nodes that come before it in the dependencies. So if we start at a node that has no incoming edges, then we can't violate any of these dependency requirements. So I might start at a node like 0 and then run BFS. And you might see already that this isn't going to quite work. Now, why might it not work? Well, it only explores the part of the graph that's reachable from 0. We didn't include this 2, 5, and 6. And so we might need something else to help us figure out how to also include these other vertices. So this idea did not work. So the next idea is maybe let's try to keep this BFS idea around, but we need to make a modification. So since there might be multiple points that are kind of act as starting points, meaning that like there are no dependencies to that node, maybe we can extend this to run BFS multiple times. So my idea is run BFS starting from each node that has no incoming edges. So first run BFS starting from 0, and then run BFS starting from 2, the next set of vertices that don't have any incoming edges. So my question to you is, does this idea work? Why or why not? Take a second to think through, is this going to work, in particular for this graph I just showed? Okay, so hopefully you had a second to think about that. Well, I would say here that this is not going to work. And the reason is it doesn't actually work for this particular graph. Notice the ordering I just came up with as the result from this algorithm doesn't respect all of the dependencies. So if I draw out this ordering, including all the edges that we included, there are some edges, like 3 coming before 2, that are not allowed based off this graph. And that's because we weren't considering this like 0 and 2 at the same time. So it doesn't respect all of these edges at once. So we're going to need a maybe potentially very different idea. Now, what I'm going to kind of hint at is that it's not necessarily BFS that's the problem. It's that BFS isn't guaranteed to work on this particular problem in this input. And so what we're going to start considering is kind of going back to last Friday before we got the election results. Way back then, we talked about this idea of a reduction. changing a graph or changing your problem so that it works with a pre-existing algorithm. That's going to be our idea here, is let's try to change this graph so that we are able to use it in BFS without having to modify BFS. So that's going to be kind of our key idea starting in the next video. So how can we use this idea of a reduction to help us solve this problem? And then explain kind of what is this reduction in the first place?